Welcome back, folks. This is this should be the final segment for section 6.2. I think this is segment number 4. When I had previously finished it, I had misplaced a page of my notes, and there's actually a very important group of equations that we cover in this section, and I debated maybe just pushing them into the section 6.3 because it's really, really short. But I know that you've got a homework assignment to actually use some of this stuff. So I'm going to go ahead and put this in here, which is where it should be. So first, let me just say that we've covered all of the kind of normal sorts of algebraic processes. We may do a little bit of refresher, but now what we want to do is we want to start incorporating, let's see here. We want to start incorporating the identities that we worked, or some of the identity techniques that we worked on in chapter 5. So this is, again, section 6.2, and I believe this is page 13. So let me kind of explain what I mean by that. There's a couple of major sorts of common kinds of problems that you might see, and let me just write one down and kind of show you what I'm talking about. So secant squared of x equal to 2 tangent of x plus 4. Now, see, the problem here is we've never talked about how to do this with two separate functions unless that they're sort of trivially factorable, and this is not. So what I see when I'm looking at this is I say to myself, okay, I want to be able to get rid of one of these trig functions through some kind of substitution, some sort of an identity. And there happen to be a lot of them in this chapter where that's exactly what you can do. So you can write secant squared as 1 plus tangent squared, and then you have the sort of normal looking quadratic trigonometric function. So that's using these identities to get us a little bit further down the road. So if I make that substitution, I've got secant squared is equal to tangent squared of x plus 1, and we're saying that that's equal to 2 tangent of x plus 4. Okay, and so now we move this into sort of the quadratic looking form. We have tangent squared of x minus 2 tangent of x minus 3 equal to 0. And I think that might possibly be factorable. I think it probably is. So let's go ahead and give it a shot here. So we've got tangent of x, probably plus or minus, well, since it's going to be, just pick one, this will be plus, and tangent of x minus something. And the product of these two things on the end have to equal -3. So I'm thinking maybe 3 and 1. I think that gives us the right cross term, and this equal to 0. So now we have two equations. We have a tangent of x equal to -1. It comes from this branch here, or tangent of x equal to +3. Okay, so the solutions that come out of tangent of x, remember with tangents, it's actually pretty easy to work with them because all you're really doing is you tweak the period. So x will be the inverse tangent of -1, which happens to be -pi/4 plus pi times n. Okay, now this one here, on the other hand, is not a known value, and so we're going to end up with something really bizarre. And I'm going to pull out my calculator here and show you how to get it. So I want to take, first off, I want to make sure that I'm in the radians mode since we're doing these in radians, and then I'm going to take the inverse tangent of 3, and it says that that's 1.249. I mean, usually the book says take that to 4 decimal places. It doesn't really make a whole lot of difference to me. So what we've got then is that x is equal to this 1.2490 plus pi times n. And I'm just going to hold that for a second because we're going to have to come up with a numeric value. This is really the first one where we've got numeric values that aren't some kind of really slick, you know, like multiple pi or something like that. So talking about the typical range that we look at between 0 and 2 pi, we've got two solutions here, but neither one of them is that negative pi over 4. So we've got x is a member of the set that contains, well, if we add 1 pi to this, we get 3/4 pi. That's the first answer. And add another pi to this, we're going to get 7 pi over 4. And then we have this 1.2490 business, approximate. And then I'm going to go ahead and add pi to that. And there's another solution. So 4.3906. And that is the solution to that problem. Kind of a slick way to deal with this, where you take, you know, you recognize that there's a Pythagorean identity going on in here, and then you make an appropriate substitution, moving it to just one type of trig function, although it's powers, but you know, that's no big deal. So there's a couple of let me try another type of problem that is that's maybe a little bit trickier, because it's not a Pythagorean identity by itself. But I'll do it with one that's relatively easy. Let's take let me do this. How about 2 cosine of x plus 2 sine of x equal to 1. Okay, so that looks, I mean, that kind of looks like a Pythagorean identity, but it isn't quite. So the thing that I'm gonna suggest is that remember that these things are, they're all like square roots, right? I mean, we can write sine in terms of cosine if we wanted to. We're going to end up with something that has, if we try to substitute write sine as a function of cosine, we're going to end up with this plus or minus in there, but it'll be plus or minus the square root of 1 minus cosine squared. And that right there becomes what you may have really hated in algebra, which are radical equations. So rather than deal with a radical equation and then try to do all this other sort of stuff, we know what the process is for solving radical equations is that you isolate one of the radicals and then you square both sides, or you maybe raise the power 3. It depends on exactly what the index is on the radical. But for square roots, you would just square both sides. So I'm gonna do that. I'm gonna split these two apart, and then I'm going to well, I mean, I could just square both sides here, but I end up with a product that I don't really necessarily want. I'll get like sine times cosine and some stuff, which isn't totally impossible to deal with, but I'll do it the way that's a little more comfortable for me. So what I'm going to do is I'm going to take the sine, the 2 sine x, and push that to the other side. So I'll have 2 cosine of x equal to 1 minus 2 sine of x. And then this is where I'm going to square both sides. Now remember, when you square both sides of an equation, it is possible that you are creating solutions that are false. So you have to go back, anytime you do this process, square both sides, you have to go back and check every single answer to make sure that it works. Okay, so with that in mind, we're going to square both sides here. We have 4 cosine squared of x equal to 1 minus 4 sine of x plus 4 sine squared of x. Okay, so this hasn't really necessarily gotten much cleaner, but we're now looking at something that looks a little bit like this previous problem, where we can make some kind of a substitution because the things are in the right form now. So what I would suggest is since this side is already a polynomial in sine, we should substitute here. So we've got 4 times 1 minus sine squared of x equal to 1 minus 4 sine of x plus 4 sine squared of x. And then I'm going to just, distribute here. I've got that's 4 minus 4 sine squared of x. I'm just going to kind of allude to the algebra here and get this down to a final version, which is that 8 sine squared of x minus 4 sine of x minus 3 equals 0. Now, this is in and of itself is kind of a hard problem, right? Because this is probably not factorable. In fact, I would almost guarantee it's not factorable. It's possible that it doesn't, it should have solutions though. I mean, there's going to be at least some value for which this actually works. But what do we do with that? I mean, when we have things that aren't cleanly factorable, we have to go to the quadratic equation. So the quadratic equation then applied to this particular problem, page 14 now. We've got, okay, so sine of x is going to be equal to 4 plus or minus the square root of negative 4 squared minus 4 times 8 times negative 3 all over 8 times 2. 2 times 8. Okay, so negative b plus or minus b squared minus 4ac over 2a. Okay, so let's simplify this sort of goofy radical looking expression. We've got 4 plus or minus the square root, well, that's 16. And I'm just going to pull my calculator out because I don't want to screw this up. So 4 times 8 times 3 plus 16. It's going to be a square root of 112, which we can probably simplify down a little bit. But here's the thing. I already know, and it's all over, it's over 16. So I don't know that it's really necessary to simplify it down because I'm going to get just a numeric value here. The first numeric value for the plus branch, I'll just kind of, so you have two solutions which are approximately 0.9114 and some stuff, right? That's one of the answers. And so I'll come back for the other one here in a second. So if this is the case, then x is equal to the inverse sine of that number, 0.9114, plus, and we're doing this in radians, so 2 pi times n. Also, x is equal to pi minus the inverse sine of 0.9114 plus 2 pi times n. So let's calculate what this value is, this inverse sine. I'll take and I want it in radians, gotta make sure I'm in radians so everything's all lining up. So I've got inverse sine, so that number is about 1.146 something, something, something. So, and so I'm gonna get from this, I've got, given our sort, this is actually the exact, I mean, this is the result right there. But if we want to find the values that are between 0 and 2 pi, the first one is this 1.1467 something, 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 right? It rounds up to 1.1468. So maybe I'll put it in as that because we need to give it some kind of a value. Alternatively, if I plug in for this one, that'll become negative. And then I'm going to add pi to it. and I end up with the alternate root is 1.9948. And there is some other stuff after there. But remember, I have to check these, so I'll have to have something to be able to plug in. Now, I also said there was another answer over here, but there's another answer, and that's from the minus branch. So 4 minus the square root of 112, then divided by 16 is going to be negative 0.4114 . So similarly, you have to consider these solutions as well. X equal to the inverse sine of negative 0.4114 yada yada plus 2 pi times n. That's one possible answer. Or X is equal to pi minus inverse sine of this negative 0.4114 and some change plus 2 pi times n. Okay, so let's see what this quantity gives us. When I take the inverse sine, it's going to be a negative angle, and the negative angle happens to be negative 0.4240, and on and on and on. So what I'm going to, because that will be outside the range, I'm going to go ahead and just add 2 pi to that right now, and I get an answer of 5.859, rounds up to 2, so I'll just call it 2. Then alternatively, see if I can subtract equals. So back to my change the sign on that number. That this, remember, this again was negative 0.4240 something. So I'll change the sign here. I've got 0.4240 plus pi, and I get a possible value of 3.5656. Okay, so like I said, I need to go back and make sure that in the original equation that those answers work. And I'm going to go back to this original equation right here. So I might as well, since I've already got it sitting on my calculator, I'm going to go ahead and try the fourth one, try the last one first. So I'm going to plug it in for X here and here. So let me take a cosine of that number times 2, and then sine of that number, and that, I might have screwed that up. Okay, recall 1, so take the cosine times 2 equals, okay, and then plus sine of that. So it ends up being some totally goofy value of negative 2.645. So what I determined from that is that this is not a possible solution. Let's check another one. Since I'm going to have to plug them in anyways, I'll start back up here at 1.1468. So 1.1468, take the cosine of that, multiply by 2, and then add to that the 1.1468 times sine times 2 equals. And again, this one also gives us that weird value of 2.6457. So it's also not one of the results. 1.9948. Let me take the cosine of that and multiply by 2. 1.9948 sine. And this one actually works. When you plug this in, I mean, you're going to get a little bit of rounding because we didn't put all the digits in here, but this one actually works. And I'm betting that this one will too. So it's 5.8592, take the cosine of that times 2. And then add to it 2 times 5.8592 sine. And again, aside from a rounding error, this one does give us 1. So the net result is that we eliminated 2 of these because they just simply didn't solve it. And we have that x is a member of the set that contains 1.9948 or 5.8592. So pretty hard problem, took a long time to get to it, but this is probably as challenging as they get. So I think with that, I think I can, there's not a whole lot of extra problems. You'll get to try some. I don't want to make everything too simple. So there's a number of these kinds of problems that are set up in the homework for this section. So when you guys get to it, feel free to ask me if you need help solving them, because they can get quite tricky, especially when they start involving identities. So with that, I will bid you adieu, and we'll see you in section 6.3.